Okay. Good afternoon and good morning maybe to some people. So I think we can start the tutorial. I won't work out every problem. I will only work out the problem, the ones that most of you had problems with. Okay. So let's look at the question. So this is the first question: 12 equal charges situated at the corners of a regular 12-sided polygon. What is the net force on a test charge at the center if R is the distance from the center to any of the 12 charges? And then what is the okay. And then the second, if one of the 12 charges is removed, what is the force on Q? This is straightforward, but there are a number of mistakes that some of you made. The first thing is the force. Is it a scalar or a vector? So when we talk about force, is force a scalar or a vector?
No.
Okay, so force is a vector, right? So let's look at the problem. I won't draw everything. So you have the face of a clock like this.
Yes.
Okay. So there's a charge Q at the center. Okay, let me try to be more sophisticated. Okay. Okay. You have so this the face of a clock, and then charge Q is at the center. So I'll put Q at the center. Let me try to do it. Okay. So sorry, big Q. So at 12 o'clock, there's a charge here, Q. At 6 o'clock, there's a charge here, Q. Okay, and you can reproduce all the other ones. So let's imagine that Q is a positive charge. So you can see that between big Q and little q, there will be a force of repulsion. It will be along the line joining this to this. There will be a force of repulsion on Q. So this will be the force on Q due to this little q. So you can see the force is downwards. You can do the same thing for the force on Q, on big Q due to little q. Okay. So I join them like that. Then there will be a force of repulsion between Q and Q, between big Q and little q. There will be a force of repulsion. What does it mean? A force of repulsion means big Q will move away from little q, and little q also will move away from big Q. Okay. So this is the force of repulsion. When we did the one for between Q here, let's call this Q at 12 o'clock. Okay. And this one, I'll call it Q at 6 hours. So I'm just showing two of them. So between Q at 12 o'clock and big Q, there will be a force of repulsion on big Q due to Q at 12 hours. So that's this force that I've drawn here. Okay. And this, because that's the repulsion, so I'm assuming that this little big Q is positive. Okay. So between big Q and little q, there's this force acting downwards on big Q. On little q, 12 o'clock, there's this force also. This force on little q due to big Q. Okay. So this force and this force, they're equal but opposite. But this one acts on little q, okay, whereas this other one acts on big. Okay. But the main thing is that the force on big Q due to little q at 12 o'clock is downwards. And then you can do the same thing. The force on little q at 6 o'clock due to big Q, okay, that force is this way. So this is the force on little q that is caused by big Q, is downwards. Okay. But then the force on big Q that is caused by little q is upward. So this is the force. Okay, this one is from the force at 12 o'clock. What I mean by 12 hours is this charge is at the 12 o'clock position, and this little one below is at the 6 o'clock position. Okay, so the force on big Q due to the one at 6 hours is this one. Okay. So you can see that this force and this force, they're equal but opposite. So they cancel. So you can do another one. You can put one here. Let's put one here. Q at this is 9 o'clock. Okay. And on the other side here, I'll put one, which is Q at 3 o'clock. So you can find the force on big Q due to the one at 3 o'clock is in this direction. Okay. And then you can find the force on big Q due to the one at 9 hours and is in this direction. Okay. So you can see that the forces are equal but opposite. When you add them together, then you get 0 because the forces are equal and opposite. Not because of the magnitude, but because the forces are equal and opposite. If you like to do it mathematically, you can find the force. Let's do first due to this, the two of them, the one at 12 o'clock and the one at 6 o'clock. The one at 12 o'clock will be, sorry. So let's find the position of the person at 12 o'clock. Okay, so the force on Q due to the Q at 12 o'clock is K, which is 1/4 pi epsilon naught. Okay. And then I have to find Q times big Q, and I have to find R. Okay, that's the minus R prime over modulus of R minus R prime cubed. Yeah, okay. So in this that I've done, so that's, and then the force at Q on Q due to the one at 6 o'clock. Actually, let's use the same formula. Okay. The only thing that will change is the position. Okay. So R equals position of Q. Okay, and is the origin. Okay. So let's find the position of the Q at 12 hours. So we'll just write it as y hat times R. Okay, that's the position. And then for the one at 6 hours, the position, so for Q at 6 hours, the position is just minus y hat times R. Okay. So if you add the force from Q, okay, at Q is 12 hours, I'll use this same formula, but so it's 1 over 4 pi epsilon naught. Q times Q, R is 0, R prime, so R is 0. R prime now, because it's at 12 hours, R prime is y hat times R. Okay. And then R minus R prime is 0 minus y hat R modulus Q. Okay. So this will just give you Q times Q over 4 pi epsilon naught. Okay. And it will be minus y hat R. Okay. Over, I take the modulus of this will give me RQ. Okay. If you do the one from Q at 6 hours, is the same, is similar, it's Q over Q 4 pi epsilon naught. And then you have 0 minus the position of that one is minus y R hat. And then you do the same thing. Okay. So whether you're mathematically inclined, so this will give you exactly similar stuff. So just Q 4 pi epsilon naught. Okay. This will be y hat R over RQ. Okay. So when you add these two forces, so when you add this force together with this force, you can see that you get 0. Okay. So you're going to get 0 because here you get 0. So the main thing is the forces are equal but opposite, and you get 0 each time. So this is straightforward. So whether you are physically inclined, if you are physically inclined, you can just look at what is here on the left. Okay. So if you are physically inclined, you can just look at this one on the left. Okay, where I explained that the forces are equal but opposite. If you are mathematically inclined, you can look at the one on the right, where you write all the forces and you see that you add them together, you get 0. So if you write something like this, sum of Q times Q over 4 pi epsilon naught R cubed or R squared, okay, and you say this is 0, this is totally wrong. Okay, this is not 0. So if you write this, F is this, first, this is wrong. Okay. Okay. Sorry, this is wrong. The reason is F is this F, I've written it as a scalar, is the magnitude of F, right? Okay. So this one is sum over I, Qi, Q R minus Ri over 4 pi epsilon naught, magnitude of R minus Ri Q. Okay. So this, because R is 0, the position where, so this will give you sum over Qi, Q minus Ri over, this will just be Ri cube. In this case, you see that this Qi is the same for everybody. Q is the same, so it will just be Q over 4 pi epsilon naught. It will be sum over I. This Ri will be 1 over R cube. Okay. And then you have, I'll put the minus outside, and then you have this Ri. So what makes it goes to 0 is this part. Not this, not this. You sum all this, you are not going to get 0. So if Qi is all positive, then Q is up, then this is positive. Everything here is positive. There is no way you can sum many positive things and get 0. Okay, just will not happen. So this part is the one that is 0. And the reason is 0 is because if you have R1, and then there's another one that is at, if I add R1, another one that is 1, 2, 3, 4, 5, 6. R6 is 0. Okay. And then R2 plus R R2 plus R7 is also 0. What do I mean? Here I put R1. So from here to here is R1. Okay. From here to here is R6. Okay. From here to here, this is R2, R3, R4. This is R2, R3, R4. There's R5. There's R. Sorry, what am I doing? 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7. Sorry, this is R7. Okay. So this is R3. This is R4. Okay. So I hope you understand all this. This one is R5. 11 o'clock is R6. And 12 o'clock is R7. Okay. 1 o'clock here. This is R8. And you can see that is exactly equal but opposite to R2. So R2 plus R8 is 8, is 0. Then also R3 plus R9 is 0. So in pairs, this will give you 0. So this sum is 0, vector sum. So that's what makes it 0. Okay. What if I remove one of the charges? So everybody is 0. I remove one of them. Okay. This one is the one I remove this. Okay. So this one I remove. There's a charge here Q. Okay. So when you remove that, I can write this as sum over Ri. Okay. Minus, let's say Rk is the one you remove. Okay. So in this sum now, this sum, let's say, so this is Rk, I removed it. In this sum, you see, let's imagine, let's say this is R7. Okay. So I remove it. So in this sum, R7 is missing. Okay. So now instead of having this sum Ri, then the force is still minus QQ over 4 pi epsilon naught R cube. Okay. Then in this sum, I have the sum Let's do it. I have the sum from I equals 1 to 12 Ri, but I remove Rk. Okay, so Rk is missing in this sum. So I have to subtract Rk. Okay. So this sum is already 0. So you see that you are going to get Q Rk over 4 pi epsilon naught Rq. So you can see that this force, if big Q and little q are positive, this force is exactly in the direction of Rk. Okay. So the force will be in this direction. Let me show it to you. Right. Okay. That's exactly what you expect from also a physical point of view. So the force will be exactly this, okay, and in the direction of the charge you removed. So let's do it physically. So physically, you will imagine you have something like this. So you have your origin. Ouch. You have your origin, okay, and you removed this one. So Q is here. Opposite here, there's a charge, little q. Between little q and big Q, there's a repulsion. Okay. So what does that mean? Little q will experience a force moving it away from big Q. Big Q will experience a force moving it away from little q. So you can see that the force on big Q is exactly in the same direction as the charge you removed. Okay. And then you can calculate the magnitude easily. Is 1 over 4 pi epsilon naught little q times big Q over R squared. Or if you like, you can say is, okay. So the force on Q now is little q, big Q minus, and then is minus Rk over R cube. Okay. So this one I can write it as little q, big Q over 4 pi epsilon naught R cube. Rk is R times R hat K. This is the unit vector in the direction of K. Of removed charge. Okay. So you see that you get exactly the same result, whether you think about it physically or you think about it mathematically. Okay. Any questions? Because I want to take. I think the next question, number 2, everybody had it right. But even in number, yeah.
Excuse me, did you have to show the calculation is showing how the vectors would cancel?
No. As for, if you look at what I did it in 2 ways. One, I did it physically. The other one, I did it mathematically. Either one is fine.
Hello.
Yeah. So what I did it in 2 ways. I did it physically and I did it mathematically. You can do it physically and get the result, okay, or you can do it mathematically and get the result. If you do it physically, so physically you do it, you get this, but this is not the force. This is the magnitude of the force. You have to tell me the direction. So you have to say the direction is in the direction from charge Q to the charge that's removed. So you have to describe the direction. You can't just give the magnitude. Okay. Number 2 is, some of you did a similar mistake. Like, okay, one of the mistakes that many of you did was that you write something and you don't show it on the diagram what it is. So for instance, so this is number 2. I'm going to do it for you now. Don't worry, you can't see the diagram yet. But when I'm done, I'll show you. Okay. Sorry. When I'm done, I'll show you. Just watch. Okay, so now somebody has something in the chat. Oh, okay, thanks. Okay. So we have this Q1, Q2, Q3, and you have this configuration. So if somebody just writes that, just writes something about vector R1, R2, R3. So I look at the diagram. Where is vector R1? Where is vector R2? Where is vector R3? Right? Because you don't tell me anything. Where's R1? Where's R2? Where's R3? Okay. So I'm totally clueless. I don't even know where your origin is. Okay. So this is not a good way to do physics. Okay. So the correct thing is you have to tell me where your vectors are. Okay. So I have to know which one is R1, which one is R2, which one is R3. For instance, now I don't even know which direction it is. Okay. So let's assume I put my origin here, which I ordinarily will not do. But you can put your origin anywhere. It's arbitrary but fixed. It's not enough also to just put your origin. So now somebody is going to write that R1 is y hat times d over 2. Okay. Sorry, minus y hat times d over 2. And R2 is y hat times d over 2. There's a problem again still, because you show the origin, but you don't show the axis. So you should show your axis also. You show the axis, because the thing is, I don't see how you can really solve this problem without having a picture in your mind of where your axes are and everything like that. You can't just be writing anything. So this I'll call my x-axis, and this I'll call my y-axis. So now I can say that R1 is the position of Q1. R2 is position of Q2. And then I can say R3 is position of Q3. So it should be some distance which you can calculate along x hat. Okay. Because position of Q3. Okay. So you need to like show exactly what is happening, not just show, because when you think about it also, you should think about it and think of what is happening. Draw a good diagram. It really helps every time to draw a good diagram. Draw a good diagram, label your axis, know where your origin are, then you start solving the problem. Okay. Even if you don't know how to, even if I don't know how to solve a problem, I'll still draw something, write something down, try to position something and think about it as I'm doing it. This is very important. Okay. So drawing a picture, they say, is worth 1,000 words. So just drawing, it helps you to see what is happening. Okay, this is this axis, this is this axis, and all that. The problem also with this that you have to be careful about is, what I found is that it's easier to use a formula like this, like the electric field is just sum Qi times R minus Ri over modulus of R minus Riq. It's easier to do this. I know, yes, you may say you want to use the method you use when you are in high school or college. Okay. I trust, because you're at this stage, that you know what to do in high school or college. Okay. I trust that you know it. So think about using this other approach I'm giving to you. The reason is this: with this approach, you don't really have to think so much about your vectors.
There is a constant, Professor. The
Yes.
constant.
What?
The
What?
constant.
Oh, yeah,
1
the
over
constant.
4.
Thank you. Okay, so in SI units is this, the constant. So when you do this, it's much easier to do it this way, because then you don't have to be thinking about which is canceling which one, which force is canceling which force. Okay, because some of you, what I saw is that some wrote that, they're supposed to find the electric field here. Some wrote something like this and canceled it and said, oh no, it's like this. I don't know. It shows me you're still spending a lot of time thinking about which direction and which direction. I mean, it's fine if you're in high school or you're in college. At this point, I expect you to just be able to know that you should write something like this and quickly calculate the forces. This should not take you a lot of time. So you just do this, you calculate the forces. By the time you do this, in this case, because Q1 and Q2, I think they have the same magnitude, you're going to find that because of R1 and R2, they're going to cancel, so that you will only be left with a force along the horizontal. You don't have to start thinking and trying to figure it out. This formula helps you. You just have to know the position, and then you put this and you are done. It simplifies your life so that you can focus on the more advanced stuff. Okay. This one is like high school, college stuff. But using this expression helps you to deal with it easier. It's the same thing. I give you something like this, okay, and say, what is the force at this point P? Okay. So this is lambda per unit length. If you try to use the method you use in high school, you have problems. Okay. Or even, let's say, instead of something that is complete like this, we'll decide to do something that is half complete, like maybe like this. Okay. And we say, what is the force here? Not symmetric. Okay. If you try to use the method you use from high school, you're going to spend a lot of time doing this simple problem. No, don't spend a lot of time doing this simple problem. This problem is very simple. This point, I'll call it XYZ. Any other point here, you call it X prime, Y prime, Z prime. So the electric field there is just, if you like, the sum, or if you like, integral. In this case, it will be an integral. This sum will go into an integral. And it's just K times the point XYZ minus this other point. This is R prime. The charges, sorry, I omitted the charges. So K is outside the charge over. For this continuum problem, the sum goes to the integral. Q goes to lambda. It depends. You have to decide whether it's the X if you are going along X, or if it's along Y if you are going along Y. Okay. So generically, I just call it lambda. Let's call it the T. T is not time, but this could be X or Y, depending on along which direction you're going. So this helps you. It simplifies a lot of things. Okay. If you don't do it, yes, you may get the answer, but you spend a lot of time on this simple problem. Any questions? Okay. For number 3, determine the electric field. I think because it's one dimension, I think everybody will get the right answer, and it's not a big problem. For number 5 is a flat circular disc. I said number 6, you should make it a ring. So you can do either one. You can use the same approach also. Let's do the one for a disc. The one for a ring is simpler than the one for a disc. Okay. So let's do the one for a disc. So I'm going to put the disk in the XY plane. So I'm vertically above it. So my position here, P, let's call it 0, 0, 0. So I'm going to take a small slice of a circle like this. So 2 concentric rings. From here to here, I'll say is S. And then this part is ds. Here I'm going to call out. I'm going to call this phi. Okay. So I'm going to just take this small piece. Okay. The area of this small piece, you can check. Okay. So it's a small piece like this. Okay. This length is ds. Okay. This arc length is, oh sugar, I made a mistake. Sorry. This is not what I should do. What I'm supposed to do is, let me clean all this. Okay. This is phi, but I'm supposed to take a small slice. So this angle is the phi. So I'm just going to take this small part. Let me shade it in green. I'm just going to take this small part. This small part is what I've done here. So this small part, I'll redo it. So if you look at it from the top, you're going to get something like this. And it goes there and here. Okay. And this small angle is the phi. And then it's going to have a thickness like this. This is the S. Okay. From the origin to this point, let's call this point A, is exactly S. Okay. So you can see that this arc length is just S d phi. Then this small area, let's shade it in red. So this small area, it will be the length, which is S d phi, times the breadth, the S. Okay. So that's the small area. The small area carries a charge sigma per unit area. So the total charge from this small part dA is sigma dA is total charge on dA. Okay. So this is all I need. So I'll write my R prime. Okay. So my R is 0, 0, Z. Okay. My R prime is okay, if you take a point on this plane, any point on this plane, it will have an X prime coordinate, a Y prime coordinate. The Z prime coordinate is 0, so I have 0. If you follow what we did in the past, this X prime will just be S prime cosine phi prime, and the Y prime will be S prime sine phi prime, and then you have 0. So again, I use exactly the same method. The E will be the sum 1 over 4 pi epsilon naught. The charge, which is sigma dA. And then I need R minus R prime over R minus R prime modulus Q. Okay. Sorry, this is not the E, this is E, because I've integrated. If you don't integrate, it's just the E. If you integrate, is E, is the total. Okay. So I don't think anybody should have a problem with this. So let's look at what R minus R prime is. R minus R prime is V minus S prime cos phi prime. Ouch, my writing is bad. So it's minus s prime cos phi prime minus s prime sine phi prime, and then is z. So I can find modulus r minus r prime cube. You can find it, you can convince yourself that is x squared, s prime squared, yeah, plus z squared to the 3/2. So I put everything there. So E will be the integral. S prime will go from 0 to big R. Okay, the total radius is big R. Okay. And then phi prime will go from 0 to 2 pi. Okay. So you see now with this, I can already think of a problem to give, that instead of having the full disk, you have a portion of the disk like this. Okay, and you're able to find the electric field at some point. Okay, say above or below or wherever. Okay, so it's not a full disk, it's a partial disk like this, and a portion is eating out. Let's say the portion that is eating out is phi. Ouch. I hope you saved it. Sorry, please hold on. I have many things I have to write. Okay, so I'll write, I'll be patient. So it's one, sorry. I'll be more careful next time. So is the charge. So is sigma dA. Actually, I should call this dA prime, because this will be s prime, d phi prime, ds prime. Okay. And then I have r minus r prime over modulus of r minus r prime. Okay. And r minus r prime, you look here, is 0, 0, z, so this will give you minus s prime cos phi prime minus s prime sine phi prime, and then z. And you can find modulus of r minus r prime cube. So that will just give you s prime squared plus z squared to the 3/2. So I can do this integral now. So sorry, so again, this is not d, this is e. So the total e is just 1/4 pi epsilon naught. Integral sigma is, in this case, sigma is constant, so I can bring it out. If sigma is not constant, you leave it in. For instance, for a case where sigma is not, say cos phi, okay, you can't take it out. Okay. You have to leave it inside and do the integration. In this case, it's a constant, I can take it out. So your r prime, sorry, your s prime goes from 0 to big R. Your phi prime also goes from 0 to 2 pi. So I was saying, one could give you a problem where the disk is not full, but the disk is cut out like this. So maybe this is delta phi. This is not exactly okay. So let's say delta phi. This is more like 75 degrees. Okay, maybe. Not exactly 90 degrees. Or let's make it 90 degrees. Okay. Ouch. Sorry. So someone stole the quarter of the pi away. So what's the electric field at a point in the system? Okay, so you give a point, then you should be able to do it also. In that case, your integral will go from here. Your integral will go from here which is phi is pi over 2, all the way to here, which is 2 pi. Okay. So you have to think about the problem. In this particular case, it's just this, and then you put all these that you have there. So it's s prime, d phi prime, r minus r prime is exactly this. If you're an astute mathematician, well, you don't even have to be an astute mathematician. And then this is z, comma z. And the denominator is s prime squared plus z squared to the 3 over 2. So you see, if you do the phi prime integration, because you have cosine phi prime, the rest does not. Okay, so if I do the phi prime integration, it will be integral the phi prime. S will be outside, s squared, s prime squared, plus z squared will also be outside to the 3 over 2. And then I'm left with cos phi prime. And it's 0 to 2 pi. Okay. And then you can do the same one for (0 to 2 pi). It will be d phi prime sin phi prime. And then you can do this similar one for the z part. I don't do everything. And then you still have to integrate from s prime is 0 to r. Okay. You can see already that this integral is going to give you 0. This integral will give you 0. This integral also will give you 0. And you're only left with the z component. So the force, the electric field here will be exactly along the z component, z direction. Okay. So it's straightforward for you to know that integral of cos phi d phi prime from 0 to 2 pi is exactly 0. Even if you don't, even if you are not great in calculus, you can already see that what are you integrating? Cosine goes this way and this way. This is 0. This is 2 pi. If you do this integral, you can see clearly that this part and this part are positive, and this part is the same but negative. So you do the integral, you are going to get 0. If you do the integral over 2 pi, okay. So you only get a z hat, an electric field in the z hat direction. Okay. If you are doing over a ring, if it's a ring, then you don't have this integral with s. Okay. For the ring, you don't have this integral with s. So it's just the phi integral, and you do the integral, you get your result. Many of you did it right, so I don't have to like rehash it. Number 7 is straightforward. You have the electric field. It's just a check of if you know Maxwell's equation, then the divergence of E. What should I write here? The divergence of E is what?
Rho over epsilon.
Yeah, it's rho by epsilon naught. So
Yeah, divergence give us the only
what?
the only value of in our direction.
Yeah, is in R direction. So you have to use the help sheet I gave to you to find what divergence of E is. Okay. Because it's in what do you call it? Is in spherical coordinates.
Yes.
Okay, so R hat
is 1
is
over
R
r square partial r. Yeah.
If you try to write it in
1 over
Cartesian
r square.
coordinates, yeah, I know. Okay, yeah. if you try to write it in Cartesian coordinates, it's going to waste your time. So if you try to write this as R is R cos phi, right? Sorry. Oh yeah, sine theta. And so this is your X R sine phi, sine theta. And this is R cos theta. And you are dividing it by R. This is going to waste your time. Oh, sorry. I thought I was showing it. Sorry. Sorry. Okay. So basically, I just did this. Divergence of E is rho by epsilon, and rho is epsilon or divergence of E. Okay. So E is given to you, but it's given to you as R hat, and then there's R cube here. Let me look at the expression. Okay. So this is the expression. If you try to use Cartesian coordinates, you are going to waste your time. Yes, you get the right answer, but you will waste your time. So it's better in this case to use spherical coordinates. You look in the sheets that I gave to you. Let's look at the sheets. Sorry, please hold on. Okay, so you look at the sheet I gave to you. Let me magnify it. 200%. So for vector identities in spherical coordinates, yeah, the divergence is exactly this. Okay. So if you don't look in the sheet, so you can see that. Let me write it down. So the divergence of V is 1 over R squared D. I'll show you what I'm writing just now. V in the R direction plus other terms. Okay, so I'll show you what I'm writing. What I'm writing is exactly this. Okay. So the divergence of V is 1 over R squared D by the R squared dV dr. Sorry, D by the R of R squared VR. VR is the vector in the R direction. So V, we can write it as R hat VR plus theta hat V theta plus phi hat V phi. So is this plus some other terms that depend on theta and phi. So note that divergence of V, so I've told you this before, is not dVr by the theta, sorry, by the R plus dV theta by the theta plus dV phi by the phi. This is wrong. Nobody did this, fortunately, but it's wrong. Okay, so this is not correct. Okay, so you have to use the correct thing. So I think everybody did it correctly. Oh, okay. So you get the electric field. I forgot exactly what you get. Okay. So the next, so once you do this divergence, you multiply by epsilon. Okay. So that will give you your charge density. Once you have your charge density, how do you find?
Actually,
What?
we get 5.
R to the what?
Squared. R squared.
Okay, thank you.
Yeah.
Okay. So you get this. So once you get your charge density, how do you find the charge? So the charge will be what?
Okay. So we consider the flux where is equal to Q over Q enhanced
No,
equal.
you don't need the flux. Once you find the charge density, you can find the charge. Okay.
Yeah.
So the charge will just be the integral of rho d3r. So that's the charge. So if I want to find charge in R, will be the integral of rho d3r, okay, from R equals 0 to R equals big R. This integral, there are three integrals. So R equals 0 to big R, phi equals 0 to 2 pi, and then theta equals 0 to pi. Okay. This is the charge, and then the 3R, the volume element, is exactly R squared sine theta, d theta, d phi. Okay. You see, the integrand is now okay. The integrand is this. You can do the sine theta integration. This is going to give you 2. You do the phi integration, is going to give you 2 pi. And then you do the integration of what is left. Okay. So you're going to be left with 4 pi. Integral from 0 to R, 5 epsilon naught, k R to the 4th, d R. Sorry, I'm missing the R. Okay, so you do this integral, which everybody can do. Okay. Any questions? This is straightforward. I really want to do some of the harder ones. Okay. Question 8. I think everybody was able to do question 8, and everybody was able to plot question 8 and everything. Okay. Make sure you really know what to do and you really understand what to do. Okay. Question 9. One of these is an impossible electric field. Which one? So you find the call. Okay, so you find call of E, and you check. Is an impossible electrostatic field. Is equal to 0 or not 0? If it's 0, it's possible. If it's not 0, meaning it's not an electrostatic field. It may be an electric field, but it's not an electrostatic field. Okay. The keyword there is static. Okay. Because from what we know, call of E is minus dB by dt. Okay. So if you have dynamics, charges are moving, or you have a time varying magnetic field, then it doesn't have to be 0. But if it's electrostatics, actually I should probably say electromagnetostatics, then call of E has to be equal to 0. So you can use that to know which one is the right one, which one is the wrong one. This time around, I found everybody did the integral correctly. Oh, okay. Almost everybody did the integral correctly. So if you don't know how to do line integrals, you should learn how to do line integrals. Okay. You can't just do the first year when I taught here, students just did the integral without doing it correctly. So they got an answer that was like twice the correct answer. Okay. So now everybody does it correctly. I assume that means you know how to do line integrals. Make sure you really know how to do line integrals. Okay, number 10A. I think everybody got it. It's a textbook problem, but with what do you call this thing? Method of separation of variables. Okay, is a textbook problem, and virtually everybody got what to do. Okay. 10B. I'll say people got what to do. I'm not sure If you spin the disk for question 6, can we treat the magnetic field the same approach? If you spin the disk, you need to find a current, and your current has to be constant. So if you spin the disk, yeah, you need to find a current, and your current has to be constant, and then you can use Biot-Savart law. If your current is not constant, you can try to use the retarded potential. Okay. So number 10, a charge density is glued on the surface of an infinite long cylinder of radius A. Determine the potential inside and outside the cylinder. Okay. Actually, for question 10, you need to know a few things. The first thing is, I gave you a problem in, I think it's homework 3. Okay. You need to show that the parallel paths of the electric field, the difference is 0, and then the perpendicular path, actually not this. What you will find is that is D. Let me raise it up again. Okay. So you need to use this expression. This, I know, oh, sorry. Let me, because I'm not sharing it. Okay. You need to use these expressions. So if you have a system like a cylinder, okay, the parallel component is along the surface. The perpendicular component, so this is D parp, okay, and this one along the surface is E parallel. Okay. So in this case, I can say inside or here, I can say this is medium 1 and this is medium 2. So your E1 parallel, in this case for a cylinder, it will be dV, the potential, well, not dV, minus dV by parallel. The parallel will have two components. There'll be a parallel. Okay, let's do this. E1 parallel will have two components. There'll be a component along this direction, and then there'll be a component along the surface, okay, along theta hat direction. The component along z direction is just minus dV dz. The component along theta direction,
Professor, can we use Stokes' theorem?
What do you mean by Stokes' theorem?
Okay. We have the integral of we have the integral of the surface. We have the curve of A ds must equal to the integral of A, the closed path of A dl.
Yeah,
can we use it?
Okay, no.
Yeah.
Okay, that's for the other. That's for the other part. For this one, you use Gauss's theorem. Okay, let's look at the problem in the homework. So I give you the problem in the homework, and you'll be able to do it with the problem. So it's homework 3. Okay, so with homework 3, you should show that this is 0, and this, the difference is equal. Okay, and also this is 0, and then this parallel one give you k cross n. Okay, so you should show this, and then once
so
you
for
show
homework 3, we use Stokes' law. Okay.
Yes.
For homework 1, we use Gaussian law, and for this we use
No.
Stokes theorem.
For homework 1,
Is
you
it
need
correct?
something from homework 3. Okay. Yeah.
Okay.
For homework
What
1,
I
you
mean,
need something from homework 3.
for homework 1, we use Gaussian law. Okay. Okay.
No. For homework 1 here. Well, okay. Let me explain what to do. I know you got the answer, but you have to think about the answer you got. Okay, so you're able to show that V is some constant, natural log R, natural log S, plus another constant, okay, plus a sum. I forgot what the sum is, cos m phi, okay, plus something sin m phi. Okay, there's some coefficient.
Yes.
I need to look it up.
We have the
So there's some
coefficient.
coefficient and some coefficient. Okay, okay. So
Our potential here depends on R and Y only.
let's look at the problem. Yeah, your potential here depends on phi. Yes.
And the position R.
Okay, yeah, so it depends on the position where you are. Unfortunately, you can't use Gauss's theorem for this because you don't have the symmetry that you need. Okay, so you can't use Gauss's law for this because you don't have the symmetries that you need. Gauss's law you use when you have symmetry. Okay, for instance, if sigma is constant, you can use Gauss's law. But in this case, sigma is not constant. Okay. Sigma in this case depends on phi. So you can't use Gauss's law. Okay. So the potential at any point, in this case, it will depend on S and it will depend on phi. And this potential is given by this expression. I don't remember everything in the expression. So it involves cosine m phi and cosine m sine m phi with some coefficients which depends on S. So I don't know how they depend on S. Maybe m or s to the minus n. Okay, I can look it up and you can look it up too. Okay, so the main thing with this is you now have to apply the boundary conditions. How do you apply the boundary conditions? Which boundary conditions do you apply? The boundary conditions you apply is exactly this and this. Okay. So the parallel components of the electric field have to be 0. The perpendicular component,
we have.
Yeah. Hello?
Okay,
Hello?
that we can apply we have V out and equal to V in at R at S equal A. Is it correct?
V, well, okay. Let's think whether it's correct or not.
Okay.
Okay. So let's think whether it's correct or not. Correct or not. So this is what you have. This is what you have. Okay. This too is what you have. So what is correct is that E1 parallel. Let's call one in and the other one out. This is correct. Okay. This is 1, this is 2. Okay. What is E parallel? Okay. In this particular case for the cylinder, parallel will be any vector on this surface. Perpendicular will be this one, okay? So parallel, we have two components. It will have a z hat component, okay? And it will have a theta hat component. Sorry, is it theta hat? Phi hat component. Okay. This will be minus 1 over s v by the theta. This will be minus dv by z. So it has two components. What about E perpendicular? Sorry. Because this is the cylinder, the perpendicular component is along this direction. So that is just s hat dv, sorry, minus dv. So this should be E parallel. This is E perpendicular. Okay. Should I do this? Okay. Let's do it this way. Okay. Okay, so I have this. This perpendicular component, the magnitude of the perpendicular component, okay, I'll just call it E perp. Okay. And that will be minus dvds. So you can get that minus. So if you do this, in minus E perp out, okay, this will give you minus dvds in at s equals a minus dv out at s equals a. And sorry,
when r goes to ys goes to,
you don't have this. Actually, this is wrong. I should have this. This is epsilon naught d in. Sorry, is epsilon naught e in, and this one is epsilon naught e out. Okay. So E in is exactly this, and then I multiply by epsilon naught. This one also is exactly this, and then I multiply by epsilon naught, and this should be sigma. Okay. What about the one on the surface? The one on the surface, you do exactly the same thing. So you have to have that on the surface minus E in perp. Sorry, parallel minus E in minus E out parallel. Sorry. Equals 0. So what does this mean? That means if I do minus dv dz in minus dv dz out at the surface, this will give me 0. And not only that, if I do dv d theta minus 1 over s, I do it s equals a minus okay. This should also give me 0. Okay. If you do this too, it turns out that is equivalent to requiring that V in minus V out is equal to 0. Okay, so you can convince yourself that this is equivalent. Okay, so this is what many of you did. Just V in minus V out is 0. Okay, you need to justify it. Okay, so in homework 3, you see how to justify it. Okay. So I think I want to. Okay, question 11 problem. We did it in 2 ways in class, and you can use any of the ways in class to determine the potential. Okay, if you like, you can use the Green's function and integrate term by term. If you like, if you like, you can use the Green's function, integrate term by term. If you like, you can, even if you use the method of images, it's still the same. Yeah. If you like, you can assume a solution and find the coefficient of that solution. So either way, you can do it. Okay. So let's go to question 12. Question 12, I think many people did it right. Okay, I'll be clear now. This charge that you have is a point charge. The question does not say it, but it's a point charge. If you look in Jackson, there's a similar problem, but it's a line charge. Okay, this one is a point charge, it's just this. Okay, so of course everybody did it right. The potential here is 0, the potential here is 0. How can I make the potential on the vertical one 0? Is by placing another charge here. Okay. Minus Q. Okay, that will make this potential on this one 0. How can I make the potential on the horizontal 0? We are placing a charge here, minus Q. Okay. But you see, if you do that with this Q and this minus Q, you apply it and remove the plane, you'll find out that the potential on this plane, let's call it OP, will not be 0. Okay. On the plane OP will not be 0. Okay. So what do you do to make it 0? So you can think a little more and see that if you put another charge here, Q, okay, then now you can remove the planes and the potential along OP and along OQ will be 0. So this is the simple thing that you can do. Okay, now there's this part B that no, part D. If the planes meet at some other angles other than 90 degrees, can you still find the images? If no, for what angle theta can you find the images? For some reason which I don't understand, well, not which I don't understand, I'll be lying to say I don't understand. For some reason, many of you were relating it to the method, to the number of images that can be formed between two mirrors. This has totally nothing to do with that. Totally nothing to do with that. Yes, you get the same result. So it's like saying the work done is P times delta V, or the work done is Q times delta V. Yes, if you use the formula, you get the same result, okay? But this delta V is volume, and this is pressure. Okay? So this is exactly what you get from thermodynamics. Both of them are work done, yes. This one is potential difference. This is charge. Okay, so you can use the same formula. Oh, sorry. Arc. Sorry. So I don't know if you saw everything I was doing. Yeah. So for the B part, you can use either of this formula, you get the right answer for the work done. But one of them is correct, the other is wrong, depending on the situation. If you are doing thermodynamics and you use this other one, you are wrong. If you are doing electrodynamics or electrostatics, you use this formula, you are wrong. Okay. So the fact that the formula looks the same and seems similar doesn't mean they are the same. Okay. The main thing you have to understand about this problem is that the number of charges you have to be even. Because let's say it's odd. Let's say it's odd. You place a charge here. Okay. I say I want the potential on this one to be 0. you can arrange another charge to make the potential 0. Okay, so this is Q, this is minus Q. You can arrange also to make this one minus Q, 0. Okay, but then if you do this, there's a problem, because now if you now recalculate the potential on OP, you don't get 0 anymore. With this charge and this charge, you get 0. But when you added another charge, this one below, you don't get 0 anymore. So you see, you have to counteract it with a different charge. So the total number of charges must be even. Okay. So if you put 360 degrees, okay, you divide it by the angle theta, it must be even. So this gives you the possible angles you can use. So theta, you can use 180 degrees, which we already did in class. You can use 90 degrees. Okay. Can you use 60 degrees?
No.
Can you use 60 degrees actually? Can you use 72 degrees? Because you see, if you divide 360 by 72, you get 5. This is odd. So you can't use 72 degrees. So 360, you have to use the angle so that 360 degrees over the angle has to be even. Okay. 360 over 60 is 6, yeah. Over 90 is 4, over 180 is, okay. Can you use 36 degrees? Okay. Can you use 36 degrees? Okay. Okay. So I'll do number 13 and then we will close for today. Okay. Number 13, you already did it in question 5 or 6, depending on which one you chose. Okay. So you already did it depending on which one you chose. So this is in Cartesian coordinates. So this point P in Cartesian coordinates, I'll write it as 0, 0, R. Or I can write it as R equals R. Theta is 0. Phi can be anything, but let's put it 0 in spherical coordinates. This radius, let's call it A. This height, is R. You take a point here, I go here. The distance from P to this point, let's call this point T. Okay. So the distance PT is exactly A squared plus R squared square root. Okay. So you can do the maths and find that the electric field is along the Z axis. Is along the Z axis, and the total charge is lambda times 2 pi r over A squared plus R squared. Sorry, 2 pi A. No. Sorry. No. Sorry. I need the potential. So you can do it. You get the potential is 2 pi a squared to the power half. Okay. So this will be your potential, 2 pi a. Let me see, but I'm not. Yeah, the radius A. So the radius A, which I should write my A better. Okay. So it's radius A. Okay. So this is exactly what you get for the potential at the point R. Okay. So this potential is the potential at the point R equals R. Theta is 0. Phi is anything, but let's use 0. Okay. So that's the potential. Okay. So now, what do? I took this, instead of being exactly at the center, I shift it to a point here. Okay. Let's call it P prime. No, let's call it P tilde. And then P tilde is the point.
Professor.
Yes.
Yeah. I guess the formula of V there is wrong. Lambda 2 by A divided by this.
What should I add?
Is V equal to lambda A divided by 2 epsilon times the square root of A plus R.
Yeah. Okay, so I put a 4 pi epsilon naught. Right? So this is fine, right?
Yes, it's correct now.
Yeah, okay. Okay. Thank you, Abdullah. Okay, so this position P is different. Is R some theta, which is not necessarily 0, and you can put any phi in it. Because of the nature of this thing, of the ring, if you have azimuthal symmetry, you'll see that V depends only on R and theta. Okay. For spherical coordinates, we already saw how to solve Poisson's equation. You solve it, you're going to get something like this: AL over R to the L plus 1 plus BL. Okay, let me write it the way you want it. Okay. So this is the potential at any point R theta. Okay. So let's find the potential at R, and then theta is 0. Okay. So I put theta is 0 there. So I'm going to get this AL R to the L plus BL over R to the L plus 1. And then PL cos theta is PL of cos 0. This is PL of 1. And this is 1. The Legendre polynomials, all of them, if you put 1 there, are going to get 1. Okay, so you have this. So V at R, theta equals 0, is sum over L, AL, R to the L, plus BL over R to the L plus 1. Okay. Do you see that this potential you found before? This potential you found before is exactly the same as this one. So this is equal to this one. So this is for an arbitrary theta. Okay. And then this one that you found is exactly this one. Okay. So this is all you need to do. So you just need to equate sum L equals 0 to infinity, AL, R to the L, plus BL over R to the L plus 1 is the same thing as 2 pi A times lambda over A squared plus Z squared. Sorry, A squared plus R squared. 4 pi epsilon naught. So they're exactly, no, power half. So they're exactly the same. Okay. Now you need it for R greater than A, right? So this is what the problem says, for R greater than A. So you have to do an expansion of this. For R greater than A. Okay. And then equate, so this is the left-hand side. So equate powers of R on both sides. Okay. So if you do that, then that will help you to fix the coefficients. Okay. So that will help you to find AL and BL. Okay. So once you know AL and BL, then you can put it here. Okay. So we'll continue from exactly this the next time we meet. I'll set a time that we should meet. I think you meet Sandro, Professor Scandolo. Yeah, I'll set a time that we should meet.
Professor.
Yes.
So in that problem, we can only replace that value, the sum.
What did you say?
In the problem, we can only replace that value of the part related to the sum, and that's it.
No, you can relate. You can equate term by term.
Okay.
Yeah. When we do, when we meet, I'll set a time for us to meet. When do you meet with Prof. Sandro? You meet him on Tuesdays and Fridays, right?
Tuesday.
Gustavo.
Tuesday
Yeah.
and Thursday.
When do you meet?